Hello, viewers. Welcome to another interesting episode of the Semiconductor Webinar. Today, again, we have enthusiastic duo Bhavesh and Jayashree with us. They have earlier presented two interesting topics to you. Today, they will be presenting the displayed topic. So, without much talking, I am handing over to them. So, over to you, Bhavesh and Jayashree.
Good morning, everyone.
Good
So
morning.
today we'll learn about from how raw materials and different materials wafers are made. So wafers are generally of a very high purity of 6 and 7N. So we will learn about its manufacturing process from very scratch.
Okay, so let's start with the introduction. Firstly, we will understand what is a sand, then how a sand is getting to the inputs, like which is the ingot, and then from ingot, how it's being converted to the wafers, and from the wafer, how we are getting the complete device. As we are already having 2 3 sessions of like a wafer to device, you can go through that again if you want any doubts, you can just clarify here. So let's start with the sand to wafer. Basically, what's this? A wafer is a thin circular and a single crystal semiconductor material, basically use of silicon. And we are going to fabricate certain electronic devices on it. So in this way, why it is necessary? So basically, the key points are like electrical properties, then mechanical stability, and then the third one is a thermal behavior. So by considering these three in our mind, we are supposed to make our wafer from ingot to, from getting from ingot to complete one single wafer. Okay, so let's start with what are the raw materials and how this raw material to the advanced technology. So basically, there are certain sand or the quartz kind of material, raw material. Then we are converting into ultra high purity silicon ingots. Then with the help of the certain techniques like Zoroarsky, Floatzo, there are the multiple we are going to discuss by now. So in that way, we are going to understand how this from the sand we are able to get the ingots, and we are able to grow one single silicon crystal, and then from that single ingot we are going to get multiple wafers. So that's again processed into the multiple wafers, and from that individual wafer, we are going to get the individual finally the fabricated ICs. Okay, so let's go with the what's quality and the why it's critical. So basically, there's the crystallography and everything.
So basically, crystallography, it is a study of understanding the structure of how atoms are arranged properly. Generally, if we want to understand that how atoms are bonded and what are it is like bonded in a manner which it forms a shape of a cubic structure. And with that cubic, there are like it can be simple cubic, face-centered cubic, and body-centered cubic. But with the little dislocations, uh, change in the change in the degree or like the slight dislocations, we can understand there are several structures based on that the crystallography is there. It is very important to understand the crystallography because based on that we can understand what are its defects, and those there are materials like wafers. It is all based on how the wafers which we have created, how those are aligned and made properly, structured it properly. So basic crystallography, it is generally there are seven different shapes. First is cubic, then there is a tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, triclinic, and with that these different lattice structures, we can understand how crystallography works properly. So these atoms, the blue ones or the green ones or red ones are just atoms and it is arranged in this manner such that it can we can understand crystallography by viewing it in a some sort of image. So there are some defects which can be understood through the crystallography, which are interstitial defects can be there, substitutional larger atoms can get in it while doing all these processes. If there can be screw dislocation can be there. Then a minute crystal grain boundary can be bigger if we are not able to manage with the temperature and pressure while doing all these processes. So we need to control everything around it and make it in a proper structure manner such that the crystallography could be aligned and make a production of wafer. We can get a better yield. So that's why I need to understand crystallography before doing a production of the wafer. Now, generally, wafers are mostly in a single crystalline, but there are in crystallography there are majorly four structures: crystalline, polycrystalline, amorphous. Crystalline is mainly every atoms are arranged in a systematic manner in a single line, or we can say in a single plane. Whereas in the polycrystalline, atoms are forming the clusters, but those are arranged all together, like forming several groups. Whereas amorphous, the atoms are arranged all over the places, scattered around, and it has a spaces, voids around it. So generally, the wafers which we use either polycrystalline or single crystalline. Majorly for IC fabrication, single crystalline wafer is used. So wafer orientation. Now, generally in wafer orientation, we have three types of wafer: 100, 110, and 111. Now, these are nothing but arrangement of atoms in different planes and axes. With that, we can understand how where atoms are arranged. It can be 010, 001, or 101, 011, or anything like that. So it is basically arrangement of atoms, and it also differs in density of atoms which are arranged. Like the highest density will be 111 and lowest will be 110. So we can understand it based on that parameter. Now CZ matter.
Okay, so what's the CZ method basically? It's called Zuraski growth method. We can call it CZ method, or sometimes we are calling it puller method. Why puller method? Because in this method we are going to pull the ingot from its crucible to getting the complete ingot, so that we get a complete wafer. Okay, so basically, this instrument around, 6.5 meter tall, or around, that's tentative, and this can be configured to hold certain, melted charge of a silicon, which can be transformed into the single crystal of, certain diameters and up to certain length. Okay, so it's basically divided into the four subcategories. Like one is a furnace, second is a crystal pulling mechanism, the third one is ambient control, and the fourth one is the control system. So basically, what's the furnace? So in this furnace we can see there is a crucible. So what's a crucible? That are those silicon chunks. Okay, and then a suspector, which would be able to suspect the inside, and it would be going to remove the one, in the form of very upward direction. Okay, then the rotation mechanism. So basically, what's the rotation mechanism? There will be two rotation mechanism, from the upside and the downside. So that would be rotating into the, like, there is some certain kind of fan or slow rotating machine. Okay, then the heating element. So basically, there would be certain heaters, which would be able to heat the crucible, so that it would be melting into melting in form, and then it would be going into the upward direction. Okay, then the power supply and the chamber itself, the complete chamber and the power supply, where we are going to give the heat, the amount of heat and everything would be into the furnace. Then the second is the crystal pulling mechanism. So basically, what is a crystal pulling mechanism? So there is a shaft, a seed shaft or a chain, and the rotating mechanism, and even the seed chunks. So basically, the seed chunks are those, as we can in this video, I would be completely able to make you understand what is the exactly means. Okay, so in this, like, there is a furnace, there are the methods.
Just a second, it is not working. The video is not playing.
Yeah, it's okay. You can go ahead and explain. I think
Yes.
Okay, so basically, in this, like, there is a rod, as you can see. I mean, there is a crystal mechanism. In this, you have to I mean, the seed shaft or the that would be rotating mechanism, and then the ambient control. Basically, what is the ambient control? So there is a gas source, then the flow control, then the purge tube, and the exhaust, and even the vacuum system. There are the five different kind of control system which we are supposed to maintain, and we have to keep an eye on that so that could be monitoring, so that we get a complete the desired volume and everything into the ingot. Okay, then the control system like microprocessors, sensors, and the outputs. These are the four types. I mean, furnace, crystal mechanism, ambient control, and the control system. These are the four process how we this crystal growth mechanism is being categorized. So in this furnace, which is the crystal also, the most important component is the crucible, because crucible material can be chemically unreactive with the molten silicon. So its electrical properties must be sensitive and so pure that it couldn't react with the silicon. And even this, as this is having very high melting point, so thermal stabilities and the hardness must be inexperienced and reusable. So basically, of silicon oxide polar and this is the suspector, which is the graphite made. Okay, so this the suspector is a graphite made. So it is used to support the silica crucible and provides the best thermal conditions. So basically, why it is so? Because graphite is already having the higher temperature properties and the high purity also. So to prevent the contamination of the crystals, so it's like having a hot zone into the crucible, as it requires a very high purity. Okay, so and in this crucible also, this must be having minimum vibration and with a great precision, so that the crystal growth process and the crystal rotation process is very smooth and soft, so that we can get the ingot in a way that we are not supposed to get the damage, or with the help of like certain parts is being still left into the chamber itself. We need to make sure that it's very important to create everything. Okay, then there is argon gas flow also. We should make sure that the ambient gas, which is specifically argon gas, is directed along to the surface to cool the chamber itself when once our process is being done. Okay, and the ambient control, inert gases, hot graphite, and everything must be protected from the oxygen, so that as it's prevent from the erosion and the gas process during the it shouldn't react with the molten silicon. So that's the main step for the control or the gas which need to be maintained. And the control parameters such as like temperature, crystal diameter, pure rate, and the rotation speed, this all should be this all comes into the control system, and this should be maintained, so that we can grow a very, as you in this image you can see, there is a hot molten and there are two rotating mechanism. So think in a way that there are two in opposite direction, it's being rotating. So when it's rotating, it would be pulling up. Okay, the ingots in the crystal which is being the melt is being pulled up, and we get the complete the ingots type structure from the Zolarsky method itself. This is a one method, and the second one is like, let's move on to the second method, which is the float zone method. Is it also called like FZ method? Basically, it's used to convert polycrystalline silicon to monocrystalline silicon. There is no boundaries and no impurities. Okay. So in this FZ method, it's used for the very small type of wafer production with a low oxygen rate. Okay, and the crucible is like silicon oxide. It's also called as a quartz silicon, which is basically used, and the diameter of it's generally greater than 150 nanometer sorry, because it's this device is already so expensive device, so it's not basically generally used for the manufacturing production, but it's used for the research purpose, or a kind of we are working on the different parameters where we are supposed to check certain properties. At that moment we are using this float zone growth method. Okay, so in this, a polycrystalline rod of ECG is passed to the RF heating coils. As you can see, there are the two heating coils from the image itself. So this which would create a molten zone from which the silicon ingot would be growing upside. Okay, so the most impurities which are less soluble in the crystal would be then the molten silicon would be stayed there downside, and the upper side would be the best part of the silicon which would be growing up. Okay, so the in this way, these are going to, again, a single crystal is going to with the help of the clamping, we are going to rotate it. Again, it's the clamping, so we are going to take it into the upward direction. So this is what the float zone method is. And there are certain what we can say methods also, so that in this float zone we are getting different properties also to justify the silicon ingot process also. So there are multiple processes eventually, not only float zone and CZ, there are eventually more which would be again carried out. Okay.
Now the ribbon method. Now ribbon method, it is basically an alternative of growing silicon into like taking out the ingot part and the slicing part. Basically, ribbon method is used for making solar cells for wafer for solar cells, because it is used it makes a structure of a square like thing. It is not grown in a phase of circular circular structure, and it has a like thickness of varying from 80 to 90 micrometer to 150 to 180 micrometer, like varies from 90 to 180 micrometer, because generally for the wafer which we make for solar cell fabrication, it varies from 100 to 90 to 180 in between that. So ribbon method is basically you have pouring the silicon, and with that you heat it up and that pull it out in a structure of a square shape. Now that square shaped structure, where there are chances of getting a heated seed crystal in it, such that you can create a polycrystalline seed into a single crystalline material, and that pulling it upwards, and with that you can create a structure of a square shaped with the seed which is put in. It can be the 111 010 and then 110. So based on the orientation which we need for a solar cell fabrication, which IC do we need, based on that we can create a phase of a rectangular wafer structure. So ribbon method, it is used as a huge alternative for making a wafer, because if we while we create an ingot, and with that ingot created, that ingot, after that ingot is polished, it is sliced, it is the waste is produced at a very huge amount, and that waste which has been produced, that waste, it is very much in huge amount, and that huge amount of will be wasted at a phase where we use a ribbon method, because you just pull it, put the polysilicon material in it, you melt it, and then you pull it upward, and it is crystallized and cooled at a with that process, and we have absolutely compared to the CZ method, we have less amount of a wastage in this ribbon method. But it is not used for IC fabrication processes, because we are getting a square shaped wafer, and it is massively produced for solar cell fabrication. As you can see in this image, there is an crucible in that. Crucible can be graphite or any quartz material, and with that there is a polysilicon material which is melted, and there can we use the seed crystal for giving a proper orientation. With that, it is pulled, as it says seed, which is pulled upwards, and with the capillary fed dye we can get it upwards. And then there is induction heating coil which will melt the whole uh, polysilicon rocks, and it is pulled upward through the direction. And after a certain amount or after a certain minutes, it is cooled, and it is either cutted manually through some process, or it can be cutted through laser processes, such that there is a initially very less amount of damage. So ribbon method is making a wafer, one wafer at a time, whereas in CZ method, you can see you can get a whole ingot and then slice it one by one. But with this method, there is a very low amount of wastage, and you can do it at a good pace, and it is very much fast. Now, Bridgman growth. Now, over and all, we learn about how silicon is grown, but now we'll go through how we can grow compound semiconductors. So, compound semiconductors, we need wafers of gallium nitride, indium phosphide, even sapphire wafers are used for many objectives. So, Bridgman growth can be done vertically also and horizontally also. Bridgman growth is used for the mass production of the compound semiconductor wafers. Now, it is nothing but we have a huge amount of any compound which is not at a pure manner. It is poured in that, it is melt around melt above the melting point of that material. The graphite holder is there. There is a proper, we can say, the crucible which is used to protect the whole system around it. It is heated at a very huge temperature, and there is a pressure created that it can be stabilized at a proper manner. With that, we can introduce seed crystal in it to get a proper orientation and proper way we can pull it out. So it is basically one CZ, we introduce seed crystal or put a rod in it and then take it out. But instead of in this process, we put a seed in it, introduce it, and make a whole ingot in it. And instead of this, it can be like this. Suppose the above, on the top side it is at a heated manner, and at the lower bottom side it is cold. So you can heat it from the above, and it is melted, and the this will be at a cold temperature. And the crucible would move. Instead of getting a rod in it and it would put it out, crucible is moved, and that crucible will change the whole parameter and make a whole ingot. So it is very much like easy to make compound semiconductor wafers, and it can be done in both vertical and horizontal way. So in vertical, the top side is hot zone and the bottom side is cold zone, whereas in the horizontal, the left side is hot and right side can be cold. But there is this thing where the hot to cold zone and hot to cool, it is basically we can understand and maintain temperature such that we get a whole ingot in a proper crystalline form. So Bridgman, in horizontal manner, there can be a huge convection. The defects can be there. So horizontal is generally used for sometimes in a research purpose, but whereas in a vertical, it is used as a production line also. And the shaft is also moved in a some horizontal in rotate in clockwise direction or anti-clockwise direction. Now, Chiropolus method. Now, Chiropolus method, it is majorly used to make a sapphire wafer. Sapphire wafer is AL203. So, sapphire wafers, it is basically you put a huge amount of material of sapphire in it, or solution of AL203 in it, and then you heat it at a very huge temperature. After heating it, you put a seed crystal in it, and that seed crystal will form a ingot kind of a structure. And we need to understand that it can be not much above the melting point, but it has to be maintained around it. So firstly, we melt it, then the crystals, seed crystal is introduced. Those it is covered with the crucible, and crucible can be of graphite because graphite doesn't melt at a huge melting point. And then we heat it until we get a crystalline structure properly, and with that we pull it out like same as the CZ, but we pull it out at a very slow pace because we are not introducing gas in it to cool it down. And it is a very slow process also, we can say. Like we get 5 mm, 0.5 to 5 mm per hour, like that. So we pull it out slowly, and well, like it within a week we can get an sapphire ingot, and then we do all the polishing, slicing processes. So it is like we already know that sapphire is kind of a glass like a structure. We can go we it is transparent, we can see uh, in and out of it. And then for the cooling, it is taken out slowly and at a very, even the temperature is not just like for a thermal budget, we don't slow it down the temperature at a huge pace. We reduce it at a 1 degree Celsius at a time, or even lower than that, such that we can cool it properly, and there is no density defect can be, or pores or holes inside. Now, top seed solution growth. Now, top seed solution growth, it is nothing but we introduce, there is some solution which is super saturated solution. Now, super saturated solution, it is nothing but a solvent, a flux, we can say. Like if I want to grow gallium nitride ingot in it, so I have to add a gallium flux in it, and that gallium flux or solvent in it, and need to rotate it and melt it at some temperature, and then I will introduce a seed, like as it said, top seed solution growth. That seed will be which is introduced in it. That seed will form a crystalline structure over it, and it will mix in it. Now, as I said, super saturated solution. So super saturated solution means if it is not super saturated, it is based on two things. First is temperature, and second is pressure. Generally in CZ, FZ, everything, we need a pressure of 10 raised to 1, 10 raised to 2, 10 raised to 3. But top seed solution, we need a huge temperature to pressurize it, and even at a huge temperature, we can mix it thoroughly. With that, the solution which is made, and it can be that is heat crystal is used, and as it goes, it is mixed properly, and it is cooled slightly slowly, with the proper formation of the orientation with the crystals, and pulled it out. And that super saturated, if it not super saturated, then there is a no formation of ingot. But if it is overly super saturated, like if sometimes it overcook it, so with that we can form a nucleation, and there can be a density defects also. So we need to maintain the amount of solution which we are adding with the ratio of the seed solution which we are introducing in it. So that's how top seed solution growth occurs. And with the ammonothermal growth. Now, with the word itself, ammonothermal, we will use ammonia with some mineralizer. Mineralizer can be anything. Now, it is a very much, how would I say, it is a very expensive way of making a gallium nitride uh, ingot in it. It is nothing but suppose I have a furnace, and that furnace, which will be requiring, it has a temperature can be goes up to 2500 degrees Celsius, and it needs a huge amount of this pressure, as it says zero point 0.3 to zero point 0.4 gigapascal already. So we need a huge amount of pressure in it, and the temperature could be sustained around from 300 to 600 degrees Celsius. As the gallium nitride melts in it, with the seed crystal introduced, it will move around, move slowly. The purity, it is absolutely excellent, but with the expensive and cost, we can think of it as a with the research paper research itself, it is used because we are having absolute pure wafers with it. And ammonia and mineralizer is used to do the chemical reaction, like as ammonia, it is already present in it. Suppose ammonia and mineralizer is already present in the whole quartz in it, and the seed crystals are introduced. Now we will add again feedstock in it, or again solution can be also used. We will use it and we will heat it, and then it is same as the calculus method. We will move it slowly, as we will reduce the temperature very slow as it mineralize properly, and that mineralized wafer it can become strong, solidified properly, and cool it down the whole wafer ingot, whole ingot, and then we'll get that ingot and slice it and polish it, same as the other processes. So we'll get it out, put that feedstock aside, and then we'll do the all other processes like slicing, polishing, and everything. So after all these processes, we can understand how these wafers are made. So in CZFZ, we can understand how silicon are made. In ribbon method, we can understand how that just for solar wafers, we can produce it at a very easy manner. Easy manner in this space is like at absolute less amount of wastage compared to the CZ method, because CZ will be requiring slicing and polishing also. Instead of that, we'll get a direct wafer manufacture out of it with a very low amount of wastage. Then we come to the Bridgman growth. Now, Bridgman used for the gallium nitride and indium phosphide compound semiconductors are there. Chiropolys for the sapphire wafers are there. Then the top seed solution for to introduce seed and the solution mix out all together to make a wafer at a low temperature and yeah, with initiated proper pressure. And with that, we get a ammonothermal growth also, which is expensive, but here it gets a very exceptionally well yield and exceptionally well wafers compared to the other compound semiconductor manufacture growth techniques. So now we'll go through the slicing process.
So, as we have seen, there are multiple number of our growth ingot growing methods. So, it's necessary to now remove the extra parts and to shape the ingots. And then, after shaping it, we're going to do the slicing. So, before the slicing, there is certain kind of operation which is called the shaping operation. So, basically, what's the shaping operation is like to removing the seed and the tank. So basically, this is the ingot. As we can consider, this is a mobile hour. So this is a seed and this is a tank. We are going to remove from the. This is a complete ingot. So we are going to remove the seed from here and the tank from the its end, from that complete silicon ingot. Okay. So why this is being removed, because this portion is being fed into the resistive measurements and can be recycled again, so that we can get usage of this again in a from each process. Okay, so this cutting is done manually, or there is a certain circular saws also, and even automatically machines are being there now. So this is a slightly oversized as automatically controlled, and cannot be maintained into the size. So this growth is eventually a bit. I mean, how much amount of we need to remove it, it's depending upon the purity you require and the purity you need into the ingot. So it's like perfectly we need to maintain it. And then what's the wafer slicing? Okay, so after the grinding is done, ingot is ready for the slicing. So firstly we need to require for the surface orientation, thickness, taper and the bow. Okay, so thickness of the wafer can be fixed by the slicing of the wafer, how much amount of wafer thickness we are supposed to get. We can set a certain what we say, I mean, thickness control manually also, and automatically this is being controlled. uh, Thicker the wafer can be withstanding the thermal processes like epitaxial, oxidation, diffusion, and it would be less tendency to perform any elasticity issues or anything which is, I mean, predictable for the wafer to get damaged. Okay, and let's understand basically what's this method and how this method would be working on. Okay, so there is a diamond cutter. This wire is having diamond inside them. So that's a wire. It's already a wire diamond cutter. So that is going to be, there is automatically rotating going on from one by one to the ingots. Okay, so this wire is going to I mean, sharp, with the sharp edges of the wire, it's going to cut the ingot into multiple slicing. There are the multiple slicing. Think of a loaf, and there is a knife. We are going to cut each of the what we say the with the help of the knife, we are going to cut the wolf with the exact size and exact parameters with the same. Okay, so it's the same, but there are the manual method, and as this is a very complex method, there are the complex techniques also, how we are going to do the slicing. And if you want a certain kind of thickness like 3 inch, 4 inch, 12 inch, so there are the basically different diameters also of each wafer and how we are going to get it. Okay, and eventually after the slicing is being done, so there is one method called polishing. So basically what's the polishing? As we know, with very common terms, we know that after, I mean, we are using the shoe polish. Okay, so why it's so to get a shine and the perfect finish. Okay, so same is like into the wafer also, the polishing word itself say also, this polishing, it's like in this chemically termed as chemical mechanical polishing, CMP. It's a final step so that we can get the smooth and the perfect shape of the surface. Okay, and this polishing pad is made up of the artificial fabrics which is taken, and the wafer is placed onto the pad, and there is a certain kind of holder so that it will be holding the wafer. Okay, and some amount of pressure is being applied, while at the same time that the holder is being rotated into the opposite direction. Okay, there is a slurry which you can see in this image also, like there is a slurry with the droplets. We are going to put it, or it's manually or automatically. There are certain times we are going to control amount of the slurry which should be given to the this process eventually. So this slurry basically SiO2, which is a silicon oxide, usually dissolved in NaOH, ammonia hydroxide. So this would be working in the form of chemical reaction in this order, that any dissolved impurities and the particles. So this silicon oxide is an abrasive material in order to polish the surface. So this is called chemical mechanical polishing, because it's having the chemical component and the mechanical component. As this is getting rotated, and as this slurry is being the chemical kind of material which is being provided, so it's like having both technique, both materials and both process in a single process. Okay, uh, that this is in this way the wafer is being getting polished from the one side, and if necessary, if we want to have like a wafer polish surface from the both side, then we need to take the wafer and we need to rotate to the back side and the back flip it, and we need to do again those method of polishing getting being polished. The one side of the wafer is being the dull and the other side is being polished. So mostly for the IC fabrication, we need one side polish and the other side is dull. But in certain cases, if we require, we are going to do in that way. Okay. Uh, and even actually after polishing, the wafer are usually taken for the inspection step, so that if there is any surface contamination or the defects that are being inside the wafer, it's being removed and it's being maintained. Make sure that we are getting the complete finished wafer. Okay, and this the characterization of the inspection is being done with the help of the four probe method. So that's the one of the other again the characterization method. So how we can characterize the methods, I mean characterize that the devices, and how we get the surety about the devices. Okay, so now let's understand what's the cleaning. Okay, so the cleaning is the most important part of the wafer. uh, Eventually this is being done for fabrication, for wafer manufacture, for characterization, even for packaging. Cleaning is must necessary step for every of the domain. Reason is to get the maintained purity, to make sure that it doesn't waste our product, it doesn't waste our device. So cleaning and inspections are those things which are required in any of the from from starting scratch to the complete device. This both processes are being used multiple of times, and the properties is multiple time changing eventually. So, in this cleaning, there are certain cleaning methods, the steps. So, firstly, there is a step one, which is the dry cleaning. Okay, so I mean, the first one is the organic cleaning, then inorganic cleaning, and then again with the dry cleaning. Okay, so there is an acetone which would be removing organic impurities sitting onto the wafer. Then in step two, there is IPA, which would be removing the residue impurities which have been left by acetone onto the surface, eventually the acetone itself. Then we are going to again put into the DI water, so that if there is any particles or any contamination of IPA on the surface, that is going to be removed. Then the fourth step is like piranha solution. So basically, what is piranha solution? It's the mixture of H2SO4, sulfuric acid, and H2O2. So it's like again one method how to clean the wafer. So that piranha solution, we are going to clean with the piranha solution, and again to remove the piranha solution droplets or kind of a thing, we are going to use DI water. So we need to make it's completely hydrophobic wafer. Okay, so any droplets would also not going to stick to the wafer, it's going to be completely cleaned wafer. And then final step with the dry nitrogen gas. So with the help of the nitrogen gas, nitrogen gun is being there, and we are going to do this is a wave thing of this is a wafer and there is a nitrogen gun. We are going to remove any of the water droplets or any of the contaminants left which are being left behind into the wafer. We are going to remove everything. Okay, so this is what the cleaning is. And now let's go for I mean clean rooms. Okay, so basically what's the clean room? There are the multiple number of the, as you can see in this image also, there are multiple number of the particles cleanliness classes. So there is this is the ISO. So basically what is the ISO? It's Indian standard is code for the for maintaining the classes and to maintain the cleanliness of the classes. So basically class 10, class 100, class 1000, class 10,000, eventually class 1 6 zeros is also there. So depending upon the particle size, these classes are being identified, and the number of classes are being there. So there are multiple classes in this image. You can see each classes and how much amount of particular particles limitations are being maintained, and how much it would be going to precision level it's going to be maintaining. point 0.1, point 0.2 micro, point 0.1 micrometer, point 0.2, point 0.3, point 0.4, point 0.5, even 1 micrometer, and even 5. So this like 5 micrometer is our class 9, which is what we can say like our regularly, I mean in campus universities, this I mean class 100, after the class 100 everyone is being going to maintain. Till this class 100, class 1000 also is being maintained. Class 1000 is being maintained eventually in universities and everywhere. But if you were to certain institutional or certain places where our complete fab lab is being created and everything is there, so at there we are using class 100, class 10, and even much more cleanliness, which won't affect our wafer or our fabricated device that is being maintained. So these are the clean room and the classes of the clean room. So and this is what the clean room design is. These are the software cleanliness room. It's the design of the outer wall structure, and these are the HEPA filters. So basically, HEPA, what are the HEPA filters? It's the filter. It is going to be these filters are going to be remove flow the. I mean, think of a way. There is shower. Okay, so shower, in this shower you're going to get the water itself. This is a shower fan filter. So these are going to put certain amount of removal of the chemically, I mean depending upon on your body or anything. So as we are entering the class 10, class 11, so the clean, but still there are certain eventually the room also. So this are, as in this is software cleaning design, you can see there is a ceiling tile, then the clean room lights also, then HEPA filters which are being fixed so that the from the top it would going to push the airflow, and then it's going to be removed from the bottom side also. These are the strip doors, and this is what a software structure and this temporary structure depending upon the fab labs and requirements, it's being changed also, the clean room structure. Then we will be understanding what's the clean room safety measurements and what things should be avoided, then what should be considered, and what a person should be making sure that this is being maintained actually. Okay. So this is think of this. Firstly, we will think of this man. So firstly, from starting from the hair. So we need to make sure our hairs are being covered. Why? Because it's already having certain kind of materials. I mean, chemically reacted materials, which could eventually damage our wafer. So this is necessary. Then safety glasses. Why? Because in certain lithography or any of the what we say eye damaging, we are going for that. We are supposed to make sure that we are wearing the safety glasses. Then if for the men, from top to bottom, it's the complete gown which is going, it's necessary and it's important to wear it. And then the nitride gloves. So because of we are our hands are, I mean, our hands basically used to produce so much amount of sodium that if we touch our the wafer by our bare hands, it is definitely going to transfer certain amount of impurities to the wafer itself. So that's necessary to wear the nitride gloves also. Then the shoe covers also, as our feet also, bare feet also would be getting like there are certain chemicals also. We need to make sure that we should be as a person, we need to take care of everything, and we need to cover ourselves completely so that it's not harmful to the wafer also, and it's eventually preventing us from any of the safety protocols, or we can say safety measurements have been taken. So, and this in what we are supposed to make sure that it's being maintained. So basically, it's like I mean, clean room classification. How much, as we got to number of the classes we saw, then the airflow control, as is the HEPA filters and every other how this airflow control should be maintained so that it is being cleaned completely. Then the material selection. So basically, what's the material selection? the amount of the right material and the amount of the right material characteristics been maintained. Sorry. And then monitoring and control, again this is the most important step, because monitoring and controlling, it's basically in that way, certain times we forget what have we kept onto the machineries, and it's once being done, we are going to again process that machine, so it need to be clean again and again. So that's the monitoring and the control steps comes into picture. You need to make sure that your clean room is being cleaned every time, every after every process you need to clean that device, and after every starting of the process we need to again inspect and clean that device, so that we get the perfect finished product without any of the mistakes or many of the defects. Okay, so what could eventually affect the clean room also is like poor airflow and filtration. So if certain amount of air is already in think of it, like in class work and whatever things, okay, any of this, then what would be happening? So eventually that would affect, and eventually the flow of the air is not proper, then it would be affecting the wafer quality, quantity, everything. Then the uncontrolled humidity and temperature. This is important again, because as certain devices require a chilled temperature, and there are chillers also to maintain the temperature. There are certain humidity monitoring systems also, so that because as this machinery would be producing so much amount of heat, also we need to maintain a temperature in that. And there should be complete training of what a person should go through, like certain kind of like safety protocols. Then a person should not work alone into the fab lab, because what for God's sake, it doesn't if there is something happening, so there is someone else also to you, which could help you out. So there are certain protocols which every fab lab are having their own, so that should be maintained in even fab lab also, and even universities are also having their own this clean room parameters and protocols, everything. Okay, then for this,
So it was all. We understood about the what is crystallography, what are the different growth parameters, then how slicing and polishing and everything can be done properly. Then after that, we can say that we also saw that with that, after all these processes, it is all these processes are taken out in a clean room. So we are also understood about what is clean room, how we should maintain it, what are the safety protocols, how clean room itself is designed to make it very much contamination free. So with this, we understood how wafer manufacturing is taken out and the clean room processes also. Thank you very much. Any doubts? I hope so.
So, viewers, our guests have today presented on a very interesting topic. If you have question, you can post in the comment. I'll flash on the screen. Uh, Otherwise, I think let me change the, yeah. So that was a very interesting thing, because whatever we get in textbook, typically in SMZ, we get the CZ method, and in today's presentation, we learned about a lot of other methods which are currently practiced in the industry. So I think Siddhant Chandra has thanked you both. So uh, I think Siddhant has learned a lot from today's episode. Uh, Siddhant has mentioned that I have joined very late. It's okay, Siddhant, because this is not only live, it stays recorded in our channel. You can replay anytime. So uh, it is not that the webinar is live casted and then it is gone from the internet, no. So it will stay there. You can watch as many as times you like. You can watch, and this is my message to the other viewers also. Our the semiconductor webinar is a bit shift from the regular webinars that uh, are just not webcasted. They stay recorded so that the learning material is there for reuse. So thank you very much, viewers, for joining in today's session. We have total 3 enriched episode from Bhavesh and Jayashree. They are constantly working on creation of the materials of the semiconductor fab industry. As in India Semiconductor Mission, we are approaching more and more uh, companies who are doing the venture outs on the semiconductor fabrication. So at this time, the knowledge of the semiconductor fabrication unit is very, very much needed, and it is the need of the hour. So this way, through the semiconductor webinar, we collaborate with other educators who are eager to share their knowledge with the community, and they learn, the community learn a lot, and we continue to have more and more knowledge in compact manner. Now there is another viewer, Manoj. I think Manoj has said it's a great lecture regarding the wafer growing methods, and thank you both of you. So you are celebrated, Bhavesh and Jayashree. So respond with a smile. I think people enjoyed your lecture. So that's a, I think, great achievement for you guys. Yeah, it is the third one, and hope we will have more such interesting episodes in future. And those who have not uh, watched the last 2 episodes, I'll suggest them to watch it. And I will, since Bhavesh and Jayashree are very, very enthusiastic, I have thought to make a separate playlist of their presentations so that you don't have to go here and there. You can go to the playlist page, and from there you can go. I have not done the playlist yet. After discussing with Bhavesh and Jayashree, I'll create the playlist so that you can have the consolidated knowledge of multiple episodes. They are sharing their knowledge. I think there is another viewer. So I think Amigo. I think this is some code name, but I don't know his real name or her real name. So I think this person may be very close to you, someone. So keep it up, Jayashree and Bhavesh. So there is a congratulation from Mr. Amigo, I'll say. Okay, Amigo. So let me flash it off. And I think we'll have more and more kind of this kind of interesting episodes. And as India is venturing out in the semiconductor process, OSATs, this kind of knowledge is very much up to date and relevant to present day of need. And thank you, viewers, again. Thank you, Bhavesh and Jayashree, for joining. So we'll go back to the studio and we'll end the stream now. So thank you, viewers, for joining. Thank you. Please wait for another interesting episode of the semiconductor webinar. So bye.